Yeah, thanks to Javier. And let me start by thanking all the organizers for having set up this wonderful meeting, and especially Adrian for inviting me to give a talk, and all of you for being here. And as the title says, I will speak about gravity in various dimensions and their associated asymptotic symmetries. And I will try to do it from a sort of holographic point of view, and I will try to explain what do I mean by this. But in particular, I would like to discuss the main points of two papers. One is pretty old by now, and one is more recent. In the first one, I try to construct a general asymptotic solution of Ricci flat spacetimes given data on null boundary, on the asymptotic null boundary. And in the second paper with Prar, Mitra, Rompul, and Binatomova, we reduced this general solution to construct a minimal example of a phase space on which we have full control of supertranslation and superrotations in 6 dimensions, and in this way derive the soft theorems. So, okay, in order to be all on the same page, let me spend some time on motivations and try to convey my point of view on why these works can be interesting. And let me start from the motivation that is probably common to all of us, which is the idea that we are now in search of a holographic duality for flat space in the form that was originally proposed by Ed Witten, that basically we are in search of some structure, some theory on the null boundaries which reconstruct the entire bulk physics. And nowadays we call this structure that he called the structure X, we call it either Carrollian CFT or celestial CFT, or however you want to call it. And the reason why I'm saying the obvious, the reason why in 2024 we are all here discussing very deeply these pictures is that almost 10 years ago, Andy Strominger and collaborators, basically, and many others after them, started to understand the infrared structure of gravity and gauge theories and connect it to asymptotic symmetries. And in this way, basically providing a sort of very first example, although bottom-up, of this original idea by Witten. And in this slide, I just try to recap the story at 3 levels in gravity and up to the subleading order. Earlier in this conference, we had nice talks by Mark, Anna Maria, unfortunately was not here at that time, and Shainesh that discussed the subleading structure and loop correction, so you can go and look at their talk. And the important thing that I would like to point out is that, we understood that in 4 dimensions, gravity is, the asymptotic symmetry is more than just the standard BMS, which is the conformal Carroll group, and it contains superrotations exactly because of this connection with the asymptotic symmetries, with the soft theorems. And so let me basically tell you what superrotations are, although already yesterday Stefan drew basically the same sort of pictures and the same metric. We are dealing with an asymptotically Minkowski spacetime in the sense of Bondi, and the diffeomorphism that preserve the asymptotic form of the metric form the BMS group. So we have supertranslations which shift any point of the sphere arbitrarily along the generators of Scry, and then we have the global conformal transformations according to the original definitions. But you can extend this to get superrotations, and there are 2 versions of superrotations. The one that I like to call BT superrotations from Barnich and Troussard, and CL superrotations by Campilli and Ladda. And both of them are related basically to the subleadings of theorems. And the important part of this, the take-home lesson from this slide is that, the moment we allow for these extensions of the asymptotic symmetries, we are basically allowing for a relaxation of the boundary conditions, as we all know, and we land in a sort of notion of asymptotic local flatness. And a very neat example of this is, we won't really need this in the next part, but let me just mention it. Is like cosmic string spacetimes and impulsive waves that are generated by snapping cosmic strings, which we now understand as basically transitions in the phase space of asymptotically locally flat gravity induced by superrotations. The reason I say this is that I will mention this story again later on, but we will not actually work that much on these kind of pictures. So now that we have collected all the pieces of the 4-dimensional story, let me think about higher dimensions and why we should think about higher dimensions. Well, we know that soft theorems exist in any dimensions, and this was proven by Ashok Sen and many others, but in Sen paper you find a very general and neat proof. And so it's natural to wonder, and many authors already did, whether soft theorems can be derived from asymptotic symmetries in higher dimensions. And this problem becomes even more interesting the moment you delve into general relativity literature and you realize that in the past people claim that there is no infinite dimensional extension of the asymptotic symmetry group in higher D, and you just have the Poincare group. So we will try in the next part I will try to show why this comes about and how we go around it. But I mean, of course, there is something that is going on here. There is a sort of clash between these statements if you believe that there should be a connection between soft theorems and asymptotic symmetries. Yeah.
Realizing terms of Fourier morphs, Gordon field, and there BMS in solution. You know the.
I am speaking about
connection, but in a sense, you said that proof that there is no problem in theorems.
Yes.
I am saying that from canonical realization of BMS.
Yeah, sure, but you realize it as the asymptotic symmetry of some theory. Yeah. So yeah, so we are trying to realizing it as an asymptotic symmetry of the space-time. Yeah, sure. Yeah. Thanks for the comment. Yeah, so okay, this problem is, if you like, just a problem within classical general relativity. If you want, it's just a wave physics. But the reason, I would like to approach this problem from a more general point of view, which is what I call, thinking about the structural aspects of flat holography. If you think about the CFT, the CFT data reconstruct the bulk in the duality. And so we naturally land on the notion of asymptotically locally ADS, which is a very relaxed notion of a spacetime which becomes ADS asymptotically. And so I think it's quite an obvious question to ask how much of this kind of bulk reconstruction can be performed in the case of flat space. In the early days of ADS-CFT, people like, I think, Don Maroff, also Kostas Kenderis, have tried to do this at space like infinity. We will try to think about this at null infinity. And okay, I will provide an answer to this question. This is more like, an inspiration. It's more like the North Star to follow, I think, when addressing all these kind of questions. So, okay, if there are no questions so far, yeah? What do I say, most general? Yes. No, exactly. This is what bothered me at some point. So I said, okay, why don't we solve Einstein equations? And this is actually the topic of the next part. Why don't we solve Einstein equation figuring out what are the most general conditions? I mean, unless we want still to relax, I don't know, with divergent asymptotics and so on and so forth. But there is a meaning in which in this more general. And there are other people that have worked on this. I think Celine, Mark, more in recent years. So yeah, we can discuss later what do we mean by most general. So before I go, in fact, to this approach of searching for an asymptotic with general null asymptotics, let me tell you what happened in earlier literature. And remember, Leonard talked 2 days ago when he said that usually people, when they study asymptotics, they take assumptions, and the assumption is usually that the fall-off, the non-trivial fall-off of the field has to go like the radiation in flat Minkowski space. This is perfectly fine in flat space in 4 dimensions, but in higher dimensions, this stronger fall-off behavior basically removes the super translations. So here, it should be clear that there is some level of arbitrariness, and we will try to remove this. So I will work in Bondi gauge, which for me is this gauge here, and I will also adopt the original condition on the U coordinate that was assumed in Bondi paper. It was also relaxed by Céline and Marc in a paper about 4-dimensional gravity in 2022. But I will discuss what the effect of the relaxation of this condition is. And let me give a couple of definitions and notation. So the problem now, Einstein equations will be solved as a characteristic initial value problem, where we have to impose initial data on an initial null characteristic. And the initial data turns out to be this transverse metric. And of course, then we will also get a bunch of integration functions, which will also characterize the solution. And I will use the terminology introduced by Vinicourt and probably also by Bondi earlier on, that an asymptotic solution is basically a form of H that is stable under U evolution. And I will also call boundary conditions the most leading terms in the asymptotic expansion that I can pick more or less freely. Just as a quick comment, of course, if you pick the most general boundary conditions, which we now try to understand what we mean by this, the asymptotic killing vector that preserves the gauge takes this very well-known form. And so basically, the defining functions are just restricted by the choice of boundary conditions and fall-off behavior, which I insist it should be generated by Einstein equations as far as possible. And so you can basically play around with all possible extensions of BMS and so on and so forth. The task is then, of course, to renormalize the charges to check that it's a consistent phase space. In this specific type of gauge, sure, yeah. So let's look at Einstein equations. And these are the 4 main equations in the Bondi approach. Then there are other 2. And notice that these are equations that determine the radial evolution of the metric functions up to, given basically the radial expansion of H on a U equal constant surface. And of course, I can integrate very easily up to these integration functions. And so these 2 integration functions will be what I call part of the boundary conditions. Then there are these other 2 integration functions which satisfy the U evolution equations, as we know, and are associated basically with the Bondi angular momentum and Bondi mass aspect, which are still integrated up to integration functions basically at the boundaries of Scri. And so the only assumption that I made at the beginning in order to run this, to write this equation is just that the transverse metric has a finite limit and is generic. It can be depend on U and so on. It's not important, but Einstein equations will fix the U dependent of H0 by a conformal factor, basically. And now the question is, okay, can I find, so notice, I have to prescribe the expansion of H on U equal U0, but there is a natural way to pick H. Of course, I mean, we had a very nice and deep talk by Leonard from, defining this from initial data in the bulk and, thinking about the bulk physics. But let's try to do it holographically. So is there a preferred way by Einstein equations that generates basically an expansion of H? And the answer seems to be yes. And the main player is the 4th main equation, which you see. Okay, let me tell you later what it is, but it should be evident from here as well. And so if you basically start solving equations by just imposing the most leading data basically at this section of null infinity, then you plug them in the first 3 equations and solve for beta, W, and U. And then these solutions, you plug it in the 4th main equation, which is, notice, an equation at any order in H for the U derivative of H. So it tells you how H moves off from the initial surface. up to the integration constant, which we usually relate to the new tensor, but in higher dimensions is not so trivially the new tensor. We will see this later. And basically, this generates the later data, and you can plug them again and start the integration again, and at some point you get a form of H, a radial expansion of H, which is stable under U evolution. So you do not generate new terms, basically. And the solution is basically this mess. But luckily, there are only a few things that we need to discuss to understand it. So as I said, there are the boundary terms. In this paper, because of the coordinate condition that I assumed, this should be put to 0. Otherwise, it violates the coordinate condition. And as I said, you can check on the paper by Céline and Mark how this impacts when you relax it. The point is that this is not going to change, including this is not going to change the larger expansion, because it only contributes to the terms that already exist here. Now, notice that Einstein equations basically give me a 1/alpha log of the transverse metric automatically. So this is consistent with supertranslation for free. And it will also be consistent for superrotation as long as H1 is not U independent. And this is a statement which depends on the choice of boundary data. And okay, these integration functions are associated to the mass aspect, the angular momentum aspect, and the Bondi news. What I said at the beginning, so in 4D and in odd dimensions, because here there are only integer powers, this is going to be traceless, so it contains the right number of degrees of freedom for accounting for radiation. But in even dimension, because of the Bondi determinant condition in this gauge, this acquires a trace from this integer term. So we have to do some manipulation in order to read off the new tensor. Actually, there is not much manipulation to be done because the new tensor follows basically from the Weyl tensor. Yeah. Yeah, sorry, sure. I forgot to say, of course, in higher dimension, we have to look at diffeomorphisms of the higher dimensional sphere, basically. One over r squared, 1/r cubed, and so on. So the first, sorry? Yeah. So the first half integer power, if you run this approach, appears basically starting from the order of radiation in odd dimensions. Yeah. So where was I? Yeah. So now let's have a look at the logarithmic terms. And so these 3 logarithmic terms that are in these boxes are the only independent logarithmic terms that you find if you run this approach. And for example, this leading log will feed all these other log here. But let us make sense of this logarithmic term by connecting with 4D. In 4D, we know that there is no logarithmic term at this level. This logarithmic term is the one that was discussed earlier by Vinicourt and was also known by Bondi, and is the one that feed a logarithmic term here, which is the one that Leonard showed us 2 days ago. And so the interesting thing is this logarithmic term, which is quite new. And to my knowledge, the only other paper that discussed this in 4D, actually that assumed this in 4D as initial data, is this paper by Valiente Cron. It's a very small paper, but very recently, Dmitry Fursaev and collaborators basically showed that such a logarithmic term cannot be neglected if your wave is generated by null cosmic strings. So it's not associated to standard notions of asymptotic flatness and asymptotically flat data, but it is there. And for the rest, it is U independent in 4 dimensions and in odd dimensions. Which means that you can throw away by by appropriately picking the initial conditions. But it is non-trivial. The U dependence of this object is non-trivial in even dimensions. And let me conclude this slide by noticing 2 other things that you can find in the paper. And especially Is it already out, the version 2? I didn't see it today, Laura. Okay, yeah. So Laurent and Aldo very recently wrote a paper about the basically doing these computations in a conformally compactified spacetime in even dimensions, and the results completely match. And you have to look at the version 2 of this paper for the updated results. And yeah, so it's it's good to have an independent check of these equations that I derived long ago. And yeah, so as promised in the abstract, I would like to tell you a bit about this logarithmic term, even though it's not still clear to me what we can do about this from a holographic perspective, but there are some nice, there seems to be an analogy that can be interesting. So as I said, it is U independent whenever we have 4 dimensions and odd dimensions, odd spacetime dimensions. So we can set it to 0. While it's non-trivial in even dimensions greater than 4. And if you think about slicing the space-time with the ADS and DS slices, basically, you can connect this structure with the logarithmic term, the typical logarithmic term that appear in odd-dimensional ADS. Yeah. Sorry? So as I said, for d equal 4, this term is U independent. So you can set it to 0 if you assume. Yes, yes. So this is something. Yeah, this is something that you discuss. Yeah, but you know, in this story, you know, if you set it to 0 in 4 dimensions, then it will correspond to the fact that there is no logarithmic term on ADS3, as we know. However, when you go to higher dimensions, you know, if I have ADS5 and the 6-dimensional spacetime, in ADS5 there is, if I have generic boundary structure, there is a non-trivial logarithmic term which is related to the variation of the anomaly. And now let me show you this small example. Yeah, so I don't know. I mean, this is what Einstein equations, as I said, give you if you work from the boundary perspective. But you can always imagine that, you know, you have to generate this characteristic in the way that Leonard basically does in his theorems, and he does not see this logarithmic term, this overleading logarithmic term in 4D. And I think that the reason is that you know, it really depends on the fact that you are putting data that corresponds to non-trivial configurations like strings and so on that you know, are not standard asymptotically flat cases. Yeah. Yeah. So, okay, let me show you this small example. Let me simplify the boundary conditions, and I take a generic metric at the boundary which is not U-dependent. Then the evolution in U of H1 is fixed by the trace-free part of the Ricci of the boundary metric. And so it can be expressed in this way. This is an integration function. And the U evolution of the logarithmic part instead is given by this equation, where this RAB of Q is basically the metric variation of an anomaly action. So this is really reminiscent of what happens in ADS5. And notice that here the anomaly coefficients are the same, like A equals C. So we are thinking about writing a note with parameter about this, but the point is that whether these or not are really signals of anomalies in a dual theory, we don't know, because we missed the boundary, you know, picture, and we cannot really compare with anything as far as I know so far. But I think that this is at least a nice geometrical thing to observe and probably to think about. Okay, so yeah, so. Yeah, let me, I will turn to this now in the simplified 6D computation, but basically the radiation sits here. The new tensor sits, it's basically associated with this integration function here, which arise at order d over 2 in the metric expansion. So, okay, let's simplify a bit. And now the goal will be to basically try and understand how we can get the soft theorems from asymptotic symmetries. And we already have control on the asymptotic structure at null infinity from the previous discussion. But now we have to ensure that the asymptotic phase space is well defined. And the minimal requirement for this is that we have finite charges. And of course, we do not want to trivialize the problem. So if we do not get finite charges for these very general structures and symmetries that we want to have, we have to figure out a way to renormalize the presymplectic form. There are various methods, and there are very general methods. And on top of that, we basically ask that the renormalization is done in a local and covariant way, which I think is probably was the first time that was proposed, but I'm not sure. Maybe someone in this room can correct me. And at the same time, since you want to connect scri plus to scri minus, this procedure has to be consistent with the matching, you know? So you have to find conditions at scri plus and scri minus on the fields such that you have a well-defined matching and the charges do not trivialize under this matching. Well, so under the conditions, under the simplified condition that I showed above, this is the 6D metric that you find in the recent paper. And this equation is, you will find it in the new version of Laurent paper because we communicated with them. And so we didn't write it explicitly, but it's this one. And on top of these boundary conditions, we want to put conditions near space like infinity such that we can then match the scri plus and scri minus, okay? And the conditions are basically conditions on the Riemann tensor near scri plus and scri minus, sorry, scri plus minus, so the pass boundary of scri plus, and in an appropriate basis, an appropriate tetrad. And what this condition implies is a number of conditions on the asymptotic fields, so which are these ones. And of course, the first one implies that the boundary metric is conformally flat, and this is a homogeneous parametrization. This is a Weyl mode. This will be the superrotation mode. This condition basically fixes the integration constant in the U evolution of H1 to be this one, so it's the pure gauge part. So omega CAB, we define it in this way, and it's basically a part of the Weyl tensor as you show in the paper of the asymptotic Weyl tensor. Yeah. So yeah, basically everything stems from here, and this object here, which is traceless and symmetric, appears basically here, and this is the object that accounts for radiation, Ali. So it's, as you see, it's not just H2, but it's, you have to make a redefinition, and it's not only the traceless and symmetric part of H2, because you also have to correct, because you know you want the proper news to transform in the appropriate way under BMS. So you can either do this kind of process by finding the right coordinate transformation, or you know that you have to read this from the Weyl tensor, and you will automatically get the right answer, which is this one. And we basically put no flux of radiation near space like infinity. Okay, all these conditions imply that the metric is analytic. Let me notice that this condition is only near space like infinity, so there will be non-trivial radiation afterwards, because there is a non-trivial U evolution of this object. And the phase space up to this order is completely characterized by this data. So we have the Weyl-Goldstone, superrotation-Goldstone, supertranslation, radiation mass, and angular momentum. I'm already using the terminology that we know from the four-dimensional literature. And in the symplectic form, they will be paired in this way. And the Weyl-Goldstone, we need to throw it away because it will appear at a divergent large U order in the presymplectic form. Now. Yeah.
Sorry, Federico. So when you call it superrotation Goldstone, it's a true superrotation, meaning a divergence less vector.
Yeah.
Yes, but then you are missing the. boost. We identify this the file.
Yeah, I think it's at the end of the day. So the Weyl transformation will be basically fixed in terms of the coordinate transformation of the diffeomorphisms of the sphere. So it acquires, this Lorentz transformation will generate a non-trivial phi. Yeah.
Yes, but then you cannot throw it away.
No, you can fix. It's not an independent Weyl transformation. So you fix it. You fix it basically in terms of. So you have a delta phi which will depend entirely from the delta of chi, if you want. And so it's not an independent Weyl transformation. This is the standard Weyl BMS story, right? You are not doing it independently on top of the Lorentz transformations.
But the thing is that all these chi transforms the Lorentz.
Yeah. Yeah. Did I say something different? Yeah.
The both.
Yes.
Then chi also the super.
Yeah, I think so. I mean, it's really. I don't know if I have the equation written here somewhere. I think it's this thing here. It transforms in this way. So chi. Where did I write it? Yeah, here. So it's basically it's the thing that accounts for the transformations of you write down your asymptotic Killing vector and you have a condition that the leading part transforms under diffeomorphism. So this is just a parametrization. Now you are saying that we should not call it Goldstone, but
no, because it transforms.
I see what you mean. Yeah.
Because as you wrote, the phi transforms under super.
Yeah.
The omega will be fixed. For the chi, I'm not sure.
Okay, yeah, I see what you mean. You want to have a non-homogeneous part here.
Exactly, it should be plus YA.
I think, so okay, maybe we can discuss it later. I think you can repackage things Okay, so, yeah, basically not, and I will show you in which sense. But so, yeah, Laura. Yeah, these things, so no, okay, so I think in the previous version of the slides, probably there were some dots here, meaning that this condition implies other conditions. Among these conditions is the vanishing of the other two independent log terms, and so all the log terms from the solution space. Yeah. No, of course, you don't. We will discuss. Yeah, it's hidden in the it's hidden here, and yeah. And yeah, it's basically, this thing here is discussed in Appendix B of our paper. Remember that what we were trying to do at the time was to find the simplest phase space, because we didn't have any control about this. And then, of course, we can discuss how to include all the logarithm terms. It would be really nice. And you already took some steps in this respect. So how am I? Okay, maybe I can continue for 2 minutes just to show you the things that we were saying before. So it was crucial in our paper to realize that now that you have this structure, basically this means that the solution space that we have is related by a Weyl BMS diffeomorphism to the solution space worked before by Hollands and others, which was the solution space I mentioned at the beginning, which we will call canonical. Canonical for a reason, the Poincaré charges will be well defined in this space, and there is a coordinate transformation that you can do, which is a large Weyl BMS diffeomorphisms, and by doing this. What here? This? Yes. No, this is what they put to 0 in. Yeah, because so H1 will be determined. So H1 is determined basically by this. So the things that enters H1 transform in this way, which is the standard way, I would say. But thanks to this map, we were able to basically evaluate the symplectic form by splitting it in a canonical. The symplectic form corresponding to the canonical solution space, which is finite, and the divergent part, which is just a corner term, if you like. And okay, the details I think are not relevant in the interest of time, so we can discuss later. And just let me show you this form. So this is the finite part. This is the boundary term, which is divergent up to this order. And notice that the divergence is only depend on the boundary metric and H1, so the large gauge mode. And so the way in which once we prove that this is a boundary term, we can eliminate it by using this famous ambiguity in the phase space formalism. And yeah, we basically propose that Y has to be built in a local and covariant way to reduce as much as possible the ambiguities in picking this Y. And this idea is inspired by ADSCFT holographic normalization. This is not holographic normalization because we are not renormalizing the action, but we are doing the next best thing, which is to renormalize the phase space. And so being local and covariant, it means that it has to be built by the induced metric, and in terms of the induced metric and the extrinsic curvatures. And these objects, if you remember, they already appeared when we wrote down Einstein equations. So this is not independent. And so it's just these two objects that, in terms of which you can write Y, it's a very long expression. I think that there are 20 terms, but at the end of the day, you get this thing here. And so the reason why I said that we would like to set to 0 the independent variation of the Weyl is because it comes with this large U divergence, and also because these two in principle, C and the independent Weyl mode do not form an independent pair with respect to do not they come paired with them, and we basically decided that we want just to keep the super translation mode. And yeah, that's it. If you do this, other questions? So if you do this, okay, you get charges. Of course, you get non-integrable charges. This is no surprise. There are ways to think about whether we can make them integrable, but at the level of, if we just want to get soft theorems, we can just do what we usually do in 4D. So do the simple thing, we just restrict to the integrable part of the charge. We verify that it satisfies the GBMS algebra. Of course, it will not generate completely the BMS transformation on the phase space because of the non-integrable part that we have neglected. But this is enough for, anyway, deriving soft theorems. And at this level, once we've done all these analyses, it's really basically turning the crank and repeating the story in 4D. And yeah.
Yes. Can you go back to the previous slide? Okay, so on the first column,
so this bracket here is the standard bracket that you find by inverting the symplectic form. So you would like to call it Poisson or Dirac, yeah.
Mysterious that it closed integrable pieces.
But it's
How do you deal with this?
So I think so I think if you do the computation, you can really see that it closes, and probably so. These are charges defined near a space like infinity, basically. So all this matter with fluxes and so on, it's something that probably do not really.
Okay, so
yeah.
in a non-radial
Yeah.
close to
Yeah.
space-time.
So yeah, as an outlook, as we already said with Laurent, it would be nice to understand the full phase space. You should have a look at their paper because they include 2 of the 3 independent logarithmic terms in even dimensions. It would be nice to understand odd dimensions. In odd dimensions, I can comment a bit if you want, but yeah. Basically, from the structure that we have derived, you see that you can define BMS charges. Then the point is whether you can find the soft mode associated to soft radiation. And yeah, what I tried to say at some point, maybe there is some relation with ADS-CFT in this story. And with this, let me thank you. Sorry? Yeah. Yeah, so again, because we didn't deal with the non-integrability part, which was due entirely, I guess, to this PA here, which is associated to the superrotation near space-like infinity. But we didn't try to run your formalism following like a generalization of Ashtegger-Streubel. I know, yeah, I know, but yeah. These are all questions that, you know, once you have an example, it would be really nice to formalize and understand completely. But yeah, because it's due to the superrotation, and this is actually not surprising. Also in 4D, if you look at the paper, at the original papers by Glenn and Cedric, the BMS charge algebra, if you push that, because they work at some finite u, basically, you know, they construct, you know, the charge on a finite cut of null infinity, and so they take these Wald-Zupas fluxes, for example, by taking two different slices. But if you push this all the way towards space-like infinity, where you have defined the non-flux zone, basically, the only symplectic flux comes from superrotation. So this is the point, I guess.
Is that
yeah.
So the Weyl-Zupas flux, no discussion about the basically that you have to deal with non-integrability due to kinematic degrees of freedom.
Yeah.
And still, to follow up on Roman's question, why your superrotation anywhere then you basically integrate the flux and you can.
Well, but so I think it looked to me at the time when we wrote this paper and we received the comments that there is something similar happening in 4D as well. But the point is that the way you usually deal with this is by shifting the integrable and non-integrable parts in order that you do not have no fluxes on pure Minkowski space, if I remember correctly. And I think that there is something going on there which we do not do here because we do not want to add this layer. And yeah, this is what I can say about this. Yeah, I mean, if you want to call these fluxes, you can call them fluxes. This is the algebra under this bracket. Which okay, I don't know why I didn't show all the brackets but you know the paper, so they are there and. Well, okay, so there was I think the problem that I mentioned at the beginning. There appeared to be this sort of clash between the claim that there are soft theorems in higher dimensions, the fact that we know how to derive soft theorems in 4D from asymptotic analysis, and the claims that there is no supertranslations and superrotations in dimension greater than 4. And up to this paper in 2023, in nonlinear GR, we didn't have, I think, a complete understanding of how you can construct the phase space. So this was the main point of this project. Yeah. Yeah, yes, so because, okay, now I don't want to say something about other papers, but so in the first paper that really tried to construct superrotations in higher dimensions, they started from the first paper that they discussed supertranslation, which is this paper by Capek. They start with a spherical metric, and then they put by hand the 1 over alpha loss. And in this paper about superrotation, basically they tried to implement superrotation on this phase space, and they noticed that there was an inconsistency because in this phase space, when you have an Einstein metric at the boundary, or in fact a sphere is an example of an Einstein metric, H1 is U independent, and you know that the superrotation generates a U dependence of H1. So superrotations in this kind of phase space are ill-defined, or actually cannot be defined. And back in the days, it was pandemic. I was wondering whether by relaxing the boundary conditions and do not put any assumption, we can automatically land at some point on superrotations, and this is the case. Yeah. Yeah, of course. In higher dimensions, yes. I mean, okay. So if I understand correctly, what you're saying is that so they do it in ADS in 4 dimensions. But I guess that the reason they relax the boundary conditions in ADS is because they want to take a flat limit in which they see the BMS group appearing, right? Yeah. But the point is that in order to have radiation in an asymptotic flat space in higher dimension, you do not have to relax the boundary conditions. But you have to, in order to have the large gauge modes, and we proved that if we believe in these computations that supertranslation and superrotations are large gauge transformations, so have non-trivial charges, if you want to have them on the phase space, you automatically need to relax the boundary conditions. Sorry? Yeah, there is, I can show you it. It's like 10, 15 lines on the paper. And so it was really hard to deal with that in order to find the best way to represent it. And we needed to use the Bondi mass evolution equation to derive the soft theorems, basically. So yeah, we have it. We didn't prove whether there is a positive energy theorem in there, but yeah, I think no, sure. I think okay. I didn't look into that. I think that there is, if you remove all these large gauge transformations and so on, the Bondi mass aspect is the Bondi mass evolution equation is just the U of the Bondi mass equal to minus the news squared. So it always decreases. So but proving the positivity of the mass, okay. I'm not a mathematician. It's of that form when you simplify everything to the standard canonical phase space. This is just adding a different frame to the story. Yeah, because there is this terms depending on. Yeah.
So they are believed to be kinematic, so you can basically are related to large gauge transformation.
Yeah, you cannot.
Be careful about the statement.
Yeah. Yeah. But, so
The charge algebra then is
sure, but so the point is that we do not have any way to deal with this large U divergence that appear the moment you push everything to I0, which we wanted to do in order to connect with scry minus. Then if you tell me that we just look at the portion of scry, we can do whatever we want. I mean, we can keep that and understand whether there are Weyl anomalies on some theory on scry plus.
really, if you evolve too
Mm-hmm.
much, so maybe there's a way.
Sure.
It would be interesting because if you have
Yeah. That's if you have an independent boundary computation against which we can check, it would be great. Yeah.
Most likely it does not.
Yeah. Let's see. Maybe.
So if it doesn't exist.
Maybe again we will have something to say with Prar soon in a note about this. Well, basically they overlooked the large gauge transformations, and we know that this may not be a good thing to do. Well, so okay. In this kind of with this kind of asymptotics, which I said is the standard, what you will get from standard linearized perturbation of Minkowski space. First of all, it's not clear why you should assume it if you work in a nonlinear theory, especially since Einstein equations give something else. So they claim there is this, it's actually a very nice paper to read by Hollans and Waltz in 2016 when they show that in fact there is no there is no displacement memory effect because there is this 1/r term. And the idea is, so yeah. So, but basically what they say is the following. So suppose that I have, if I remember the argument, of course, I don't want to misrepresent. So suppose that I have this kind of configuration. This is scry plus, and here there are some gravity waves, and this is stationary and stationary. And with this boundary condition where the metric is Einstein is just the round sphere, as I said, the HU1 is equal to 0. So this does not depend on time. So even if I assume that there is an an H1 here, which will be pure gauge, pure supertranslation, I can find a supertranslation here and here that eliminates them both together. In 4D, this is not possible because H1 has a non-trivial U dependence, which is due to the wave. However, so we showed that the charges for allowing for this H1, especially when you have a generic boundary metric, are non-trivial, and so in principle you are not allowed to set it to 0. And what happens is that the graviton, the new tensor then gets redefined. It's not just the U, so the radiative mode will be H2. It's not just the U of H2, but we'll take into account this H1, which basically is, if you like, the frame dependence of the definition of the graph. Where is it? Here. So yeah. Yeah. So of course you can also associate memory effects. Yeah. But the fact that, so I mean, it was also clear before, because they also, so I think Andy and Anna Maria and Monica Pate showed after this paper that there is a memory effect always, anyway, associated to not this overleading order, but the Coulombic order. So anyways, there are memory effects in higher dimensions. So the soft theorem, the proof that was given by Ashok is general. So in any there is no distinction. This is quite funny. Yeah. I mean, in odd dimension, the issue is that you know, the wave. So if you solve like a massless wave equation in even dimensions, the characteristic is the light cone, and in odd dimension you have this sort of dispersion inside, and figuring out how you embed it in the Bondi formalism is. Yeah. Yeah. In fact. Yeah. What do you mean by null ones? Mm-hmm. Yeah. I mean, prior has some papers about higher dimensional, also odd dimensional soft theorems in the context of linear theories. So Maxwell but the case of gravity, as far as I know, is not known, especially the nonlinear case.
And I worked on that. The question is, why do we care about it?
Well, I can give you a very, you know, a big picture question answer. You know, in ADS-CFT, the standard rules of ADS-CFT do not change whether you go to different dimensions, and yeah, maybe, you know. A good question, and yeah, so this is something I honestly I've been thinking about, but not so deeply. So in the sense that I'm still trying to, you know, I understand the claims that, you know, that there are, from a celestial CFT perspective, you know, the real charges, defined as topological charges, it boils down just to the standard conformal group, you know, the global part of the conformal group and supertranslations. So these things here, as Dan Capek suggested, is like more parameterizing, like transition from a celestial CFT to another celestial CFT. I don't know in terms of Carrollian what we would expect, because we always say that the conformal Carroll group in D dimensions is the BMS group of a D plus one dimensional spacetime. Okay, what does it mean? Do we really mean that we have to take this as the asymptotic symmetry group and then build a theory which is conformally Carrollian invariant or not? But this is a question that, you know, it's too far ahead, I guess, answer, at least for me. Okay. Thanks again.